Hello everybody, and welcome to page 136 of the workbook. And in this section we're going to talk a little bit about a totally new topic, functions of two variables. Now just to introduce the general concept of this before we dive into example 1, I want to just illustrate with an analogy why we might be interested in a problem like this. Okay, so up to this point in your calculus classes, you've talked about functions of one variable. So just to give you an example of that, you might be studying something like population versus time, maybe population of a bacteria colony or something like that. And in that situation, we could write P equals f of t, population and time are related, and you wanted to study that problem, you might draw a graph of this function. Okay, and you could make a plot of time versus population, and you'd get some sort of a curve. Okay, but what if you had a situation like this? Let me just describe a similar situation. Maybe you have a mortgage, and you'd like to talk about your monthly payment, and ask what factors would influence my monthly payment. Well, maybe the interest rate on your loan and the amount that you borrow, let's say. So in this case, your monthly payment is a function of both the interest rate and the amount borrowed, and what we have here is what's known as a function of two variables. Okay, the two variables are the input variables, interest rate and amount. Okay, well, how would we study a function like that? If we wanted to graph that, we would now need three dimensions because we've got three variables involved, I, A, and P. And so this section is all about kind of how do we graphically represent a function like that and study things like rates of change. Okay, so let's scroll down here and kind of get started on that problem. All right, and so we're going to start ourselves off with a specific example of a function of two variables, f of xy equals x squared plus y squared. Okay, we'd like to get some idea of what this function looks like in three-dimensional space. Okay, so we're going to start the way that you maybe start in an algebra class. You've got a new function that you want to look at, and so one way to get a feel for what it looks like is to just substitute in some values. So we've got two input variables, x and y, and our output, z, looks like x squared plus y squared. Okay, we're going to make a table. It's going to have three columns. And since x and y are both the input variables, we need to choose values for those two variables. Okay, let's keep it simple and just try to choose some nice numbers for x and y. So we might start with just 0 for both of them. Okay, and then how about 1, 0, 0, 1, 2, 0, 0, 2, and then finally maybe 2, 1. Okay, we're going to substitute those values into our function, x squared plus y squared, and just see what we get out. So if we start with 0, 0, substitute those in, you'd get 0 squared plus 0 squared, and that equals 0. So our first point on this graph is going to be 0, 0, 0. 0 for all three of our variables. Okay, and then for 1, 0, similarly, take those two numbers, substitute them in. This time we're going to get out 1. Okay, you can probably do the rest of these. So 0 squared plus 1 squared is 1. 2 squared plus 0 squared is 4. 0 squared plus 2 squared is 4. And then finally, 2 squared plus 1 squared would give us 5 as an output. Okay, I'm going to go ahead and just circle all of those z values that we found. Okay, now how do we plot those points? Okay, well, we can do that over here to the right. We've got a three-dimensional coordinate system. Okay, and this is maybe the first time you've seen something like this. So to help you visualize this, if you're sitting in a rectangular room, you might find two walls that meet each other in your room. Okay, so maybe over here is wall 1 and wall 2, and they meet each other in the z-axis You can think of that as the line that goes straight up and down here is the floor. And you can think of the x-axis as being kind of the line that goes along the bottom of wall number 1, and the y-axis is the line that goes along the bottom of wall number 2. Okay, the z-axis just goes from the floor up to the ceiling. Okay, so if we wanted to plot the first point, okay, over here, 0, 0, 0, x, y, and z are all 0, and so that point would be sitting right here, okay, right at the origin. Okay, I'm going to erase these markings that I made. Okay, so let's replot that point 0, 0, 0. We're going to go down the list and see if we can plot those points one by one that we chose. Okay, so then second row in our table, we have the point 1, 0, 1. Okay, so we want x to be 1, y to be 0, and z to be 1. Let's find that point. Okay, so we're going to go 1 along the x-axis. We're going to go 0 along the y-axis, and we're going to go straight up 1. Okay, and so the point 1, 0, 1 would be sitting right here, kind of on wall number 1 somewhere. Okay, and then moving on, let's see. Next point is 0, 1, 1. So x is 0, y is 1. So we're going to move 1 along the y-axis and then straight up 1 along the z-axis. Okay, there's 0, 1, 1. Okay, we keep doing this. Okay, so next point is 2, 0, 4. So we're going to move 2 along the x-axis, 0 along the y-axis, and then 4 on the z is going to take us straight up 4. And we're going to end up here. All right, and then let's see. Next we're at 0, 2, 4. That's going to take us 0 along the x-axis, 2 along the y-axis, and then straight up 4. Okay, so we'll put us there. Excuse me, that's 0, 2, 4. Okay, and then finally we come to probably the most challenging point to visualize, this last one, 2, 1, 5. Okay, and our diagram's getting a little cluttered here, so I'm going to choose a different color. So we want to go 2 along the x-axis. Okay, that's going to take us to here. We want to go 1 along the y-axis. That's going to take us over to here. And then we want to go straight up 5. Okay, it's a little hard to visualize where that point is, so I'm going to draw an entire box here. Okay, so kind of just... We know that we want to go up 5, so I'm going to draw an entire box that has a height of 5 just to help us visualize that point. We'll draw the box first, okay, and then kind of use that to help us locate our point. Okay, so now that we've got that red box, let's see if we can find this last point, 2, 1, 5. Okay, so again, we're going to start at the origin. We're going to move 2 along the x-axis. We're going to move 1 along the y-axis, and then up 5 is going to take us to the top of this box. So there's our last point, 2, 1, 5. Okay, well, you can kind of see this diagram that we've drawn here. It's a little bit of a mess. We plotted a few points, and just to highlight all of those again. Okay, there they all are. We could ask the question, what would the entire graph of this function look like? Well, it's kind of hard to picture, isn't it? These plots that we pointed here, they don't help me a whole lot. So the good thing is that we have tools like Mathematica that can plot graphs in 3 dimensions very nicely. So I want to just show you a quick picture of what Mathematica's plot of this looks like. Okay, so I'm going to turn the page here. Okay, and here's what the graph of z equals x squared plus y squared looks like if you ask a computer to plot a bunch of points. Okay, this is what's known, if you want a name for this surface that we've got, it's called a paraboloid. And you can see that on this graph, I've kind of highlighted for you the 5 points that we plotted. Okay, Mathematica has showed us a bunch more. Okay, so the rest of this section will proceed by studying functions like this and exploring the problem of how would we answer questions like the rate of change of the output relative to some of the input variables.